Venga. Vamos a comenzar con esta nueva parte del congreso, después del coffee break. El siguiente speaker es Bravin, de la Universidad de Cantabria, que nos va a hablar de regularidad para las ecuaciones de stock.
Muchas gracias por la posibilidad de hablar aquí. Voy a hacer la charla en inglés, porque cuando hablo de mi trabajo, suelo trabajar en inglés, es demasiado difícil para mí hablar en castellano. En este caso. Entonces, what I'm going to talk about is this work with many people. So, Manuel and Joyce from Ciudad, Hans from Heidelberg, another from the Current Institute, and Jonas from Vienna. So let me start by some picture. So here is what we have in mind. So what we have in mind is to study the evolution of a droplet. In this case, you have to think about to have like a table. So this is the lower boundary, lower part of the boundary, and you have some water on the table. So basically, here you have surface, a free surface, and you have some equation for the liquids, and we always consider like a viscous fluid in constant to what we saw in the morning. And then one of the main difficulties of this process is the fact that here we have a contact angle. That for a physical reason, this contact angle is fixed in time. So this contact angle theta, by physical experiment, does not depend on time. And depending on the scale that you will study the problem, for larger scale, you can see that this angle from a macroscopic way, you can see that it's evolving. But at a really small scale, this angle will remain always fixed. So we don't have problem of evolution of the angle theta is fixed in our case. And what is moving is the free boundary, okay? And the goal, we would like to show well causes for this problem. And the second steps will be to study the lubrification approximation. I mean, we would like to send this angle theta to 0, and in the end, to find the equation which is describe this kind of system, which is like the thin film equation.
But you prescribe the angle from the beginning?
The angle here is fixed. This angle is fixed, theta.
But you said you can take it to 0. What does that
mean? I mean, so you start with a droplet with the angle theta, I mean, P over 3, and then you would like to, I mean, the lubrification approximation is tell you if you start with a droplet with angle theta, when the angle theta go to 0, in the end, in the limit, you will get the thin film equation.
Ah, okay.
So, I mean, you know what it is.
Okay.
So, what are the difficulties of this problem? There are many difficulties. So, as you will see really fast, we are starting with some easier problem. So, in the talk of this morning, we talk a lot about singularities. So, what are the singularities in our case? In our situation, the singularities are the angle theta. Okay. Actually, the singularity is not like the regularity of the solution, because our goal is to show existence of solutions that are quite regular. Because actually, the real singularity of the problem is that to move this contact point, we need the pressure to behave like log of r in the tip. So log of r, log of the distance to the tip. So here in the singularity of the pressure, we already know from physical reason how it involves these points. So in particular, we have already an idea how these points will evolve. If you are able to solve the problem, so we would like to decompose the problem. How we think that we can expand it, plus some reminder, and this reminder will be somehow regular close to the tip. So the goal is to show existence of like sort of regular solution for this problem, and moreover we would like to have a regular solution, an estimate that are not depending on the angle theta. Please. Okay. That are so estimate that you default on the angle theta, because if you want to send theta to 0, then of course you need to have estimate uniform data. So which are the easy situations that are considering is the following. So forget of the free boundary. I mean, free boundary is already, we have the problem just with this model. So we just take a wedge, like this. We fix an angle theta, because the angle theta will not depend on time. We forgot about the time derivatives for the moment. And we just prescribe the Stokes systems. You see here Stokes on this wedge. And then we have to impose some boundary condition. So there are many boundary conditions for the dynamic Stokes, but if I want to make this point to be able to move, I have to prescribe, I cannot prescribe the no-slip boundary condition. Because if I prescribe the no-slip boundary condition, the velocity of my particle on the bottom of the domain will be equal to 0, and so the field is stuck, so this point will not move. And so I have to consider different boundary conditions, and here is a way how to define this more general boundary condition, and this condition depends on beta. So if beta is equal to 0, then you have the so-called no-slip boundary condition. If beta is equal to plus infinity, basically the end u dot tau is equal to 0, so you have perfect slip. And this is also something that we don't want to have. We would like to consider like no-slip boundary condition. Because to get in the limit our thin field model, we need to start with the model at least on the lower boundary to have no-slip boundary condition. So we would like to start to talk about this system. On the upper part, what we do. So in general, we would like to prescribe some free surface. So we would like to consider a free boundary problem. But at the moment it's already too difficult. So we just say, okay, we take the same condition in the lower part and the upper part, and then in the future we'll see how this, how we can change the upper boundary condition. So which are the difficulties of these problems? That this boundary condition was scaling invariant. I mean, if this condition were scaling invariant, then almost everything was already known. And the fact that this boundary condition is not scaling invariant is all the issue of the problem. So how can we see where this difficulty occurs? You have to go to menu.
One second. Who is omega prime?
Omega prime. Okay, is the boundary without this point.
Ah.
I mean, yes. It's just I mean, just the full boundary, but without the point of the. So to understand a bit the difficulties, we need to go to Melin, because Melin is something easier in this case. What is Melin is just, I mean, you have to think about Fourier. I mean, Melin is nothing else than a Fourier transform, you see here, but not applied to the function, but to f e to the x. And it's a complex Fourier transform. So basically it has the same properties. So you have a partial identity. So you see immediately that you can extend the idea of HF space in this in this setting. And what is good here that you have weight. So you are able to introduce weight with this Melin in Melin. Then you have scaling derivatives. So these are scaling, RDR is scaling invariant, and this in this Melin variables, the scaling invariant derivative like behave really well. So if I derive like RDR, I get a lambda, and if I move the weight, a weight of the type R to the minus A, then this just move my Melin transform. So let's write the system in first of all in polar coordinate and then in Melin. So you don't have to look at all to this system, but I mean you can immediately see here in the second line that if you have U, for example, ignore the first, second, third, fourth equation. If you look at your function U is evaluated only on lambda. You see here only lambda, the expression in lambda minus 1, and the forcing in lambda minus 2. And this holds for the equation 1, 2, 3, and 4. But in the last one, you see that we evaluate a boundary condition in lambda and the other one in lambda minus 1. This means that you have a change of scaling. So this boundary condition is not scaling invariant. And what is known for the system, basically if you have scaling invariant boundary condition, which I mean, for example, taking an average will be a system like this, then U is defined on your lambda. Actually, you can take the first equation, you derive in phi the first equation, minus the second equation multiplied by lambda minus 1, use the divergence free condition, and these systems become a fourth order ODE in U phi. Okay? So when you have a fourth order ODE, you solve it, you write down the Green function, and then you can say almost everything about the condition, about the solution. And the same holds for the free slip. So if you have here some scaling invariant boundary condition, then you can write an ODE for UR, you can solve it, and this is what Mazia, Kozlov, and Osman did in their work. I mean, there are many works and books where they are taking this kind of system. So, for non-scaling invariant, here we are considering non-scaling invariant boundary condition. What we can do? Actually, we can prove similar result, and let me write this result like as follows. So, I mean, you have to introduce many spaces, but you also think that we are working with weighted spaces with the weight of the type R to the minus alpha. So U alpha means that is a L2 space with weight alpha. If you put here K, I put derivatives and I put some weight. Okay? So when I'm talking about this space, it's basically for me a L2 space. This is an HK space, more or less. And for the boundary, you have also introduced this space. You see immediately that I can go from this variable, like the space variable, to the menu variable quite easy, and the spectrum, by the fact that I have this partial identity, I can pass from here to here quite easily. And so what we are able to show is actually, the first result is that if I have a forcing term in L2, in a weight L2 spaces, then we can get a system of solution like in H2 for U and in H1 for the pressure in these weighted spaces. Moreover, the constant that here I'm putting does not depend on theta. So I can think to, in this case, to set theta to 0. Notice that actually here the explicit dependence on theta in the space. So maybe some of the quantity that are uniformly bounded, some of them explode, but at least with a given rate. So what is interesting for me about this? Okay, let me go to the assumption. So let me go to the assumption. So basically, which they are the main assumptions? The main assumption that I can show the result for any angle theta between 0 and pi, if I'm assuming the product of the weight for the angle small enough. So basically, the picture that I have for alpha and theta are the following. So the system has singularity in this line. Theta is equal to pi over alpha plus 1. What I mean by singularity is that basically the Stokes system with perfect slip, the Stokes system with perfect slip has a non-zero kernel on if the weight, if theta, if you have this relation for alpha and theta. So of course I cannot really cross this singularity, otherwise I can, so the kernel is non-zero, the kernel of the operator is also 0, so I cannot really cross this singularity. So I have to assume to be slightly away, so this is why there is 1 over minus epsilon here, because I want to be slightly away from this singularity. And then I have a condition that alpha theta must be less than c, so in the yellow region is the place where we are able to show a system solution. So you immediately see that I can consider solution up to theta equal to pi. So basically as close as I want to pi. I cannot reach pi, but choosing epsilon small, I can go upper and upper as I want. And then, if I choose the weight, if I choose theta really small, I can choose whichever weight I want, basically. And this is good in our sense because what we would like to study is like theta goes to 0. So when theta is really small, we have a bunch of alpha that we can choose, and this maybe will play a crucial role in the future works. So what is interesting is how we prove the result. I mean, if you think about to work, if you want to like show external solution for this system, the first main approach is to use some variational approach. And so for a variational approach, what you have to do is you multiply your system by some test function, and you do some integration by parts. What you are left is with the blue stuff. So the red stuff is on the right hand side. This is basically your energy, which is some positive linear form, and on the left hand side is the forcing term. So if you do it like in this case, I do it without width, and if I do it without width, I'm able to show like H1 dot solution. This is quite easy. But the problem is that we would like to consider solutions that are more regular. I mean, the issue is that if you are able to show external solution, and we are able to show external solution, how we can recover the pressure. I mean, it's not clear how we can recover the pressure because it's not clear that we are able to solve this problem due to the regularity of the boundary, because the boundary is only Lipschitz. And so we cannot really take traces, and so for us it's a really big issue to recover the pressure and hope one day to show a H2 solution for this problem. So, what are basically the difficulties in the unweighted setting is that basically we don't have a habitat inequality. So, if there is a weight r to the minus 2 alpha in front of my space, so I'm going to the weighted setting, then I can write down some sort of hard inequality, and this hard inequality will explode exactly when alpha is equal to 0, because this constant will behave like 1 over alpha squared. So if there is no weight, this will explode. Then the second one is traces. I mean, if you like to recover the pressure from your equation, it will be useful to have information about the trace on the boundary, because like the pressure is a solution of a Laplace problem with the some boundary condition, and you immediately see that if you go away from 0, then you can take traces. And so this tells you that maybe in this weighted setting is easier basically to improve the regularity, because I can take traces, I have some estimate, and so I can try to improve the regularity. Okay, so how one can do this? The first idea is to just multiply your equation by a function multiplied by the weight. In this way, I can get a bilinear form on the right hand side, which has some positive term. So this is the term that I have to control. But by the fact that I impose the weight, I have some commutator appearing. You see the commutator between the pressure and the weight. And the question is, can I absorb this term on the left hand, on the green term, in such a way that I can get some like a coercive bilinear form, because this is how we prove existence in the unweighted setting. And actually we notice that for some terms we can do it. For example, for this term and this term we can absorb it. But then we have really difficulties with this term. Why? Because my boundary conditions are not scaling invariant. So here, a possible approach is to use the Navier-Stokes boundary condition. So dn ur is equal to ur. Okay? You use the Navier-Stokes, but if you use the Navier-Stokes, you change the scaling. This will always be of the scaling of the bulk term. If you change the scaling, this will be a term of the. This is always be a bulk term, and this one will have the scaling of the boundary term. So basically, if you use the Navier boundary condition, you are able to absorb this one, but this is not anymore in the. But this is not in the right space to absorb it here, and not the other way around. So you are basically stuck. So one possibility is to see that here you have the n of UR, and so you can apply backwards the divergence theorem. So you make up here a second derivative in phi of UR on the right hand side. But now you say, okay, I have second derivative in phi. On the green terms that are the good one, I don't have second derivative in phi, so still I'm out. I cannot do it. And so here in this case, the idea is to consider like more complicated bilinear form. I mean, instead of multiplying your system by r to the minus 2 alpha v, I can also multiply my system by the fraction of v with the appropriate weight. And then you see immediately that this term will give some control on second derivatives. So if I sum up these two bilinear form, can I say that this bilinear form is coercive? So I'm expecting that this new term that I produce, I can absorb it here. And actually, you immediately see that if I have here there is a 1, here there is a 3, there is something which is missing. So basically, if I look to the estimate, what we are going to show is basically that B1, you can bound it by above when you are considering like trying to study the coefficient by your green term that are the nice one, minus a term that depends on d square of phi, which was appearing before. And then you can do the same. You can take B3, and then you have this good term, and the other, and some reminder. The black term, you can absorb it on the green term if you choose exactly B1 plus a constant alpha theta 3. If you choose exactly these values, then you can absorb the black terms, and then we are left with these red terms. And in the end, you notice that when you take the stock system in the wedge, and you take RDR derivatives, that this behaves really well. I mean, if I apply RDR derivatives on the stock system, you see that in the equation they will remain the same. Here they will appear sometimes in the pressure and sometimes on the right hand side. So basically, RDR derivatives behaves well with the stock system in the wedge, and in particular, you can consider the linear form of this type that are obtained by testing the equation with this function. If I test the equation with this function, then the linear form that I get is coercive, so I can show its system in the weighted setting. But this existing result is not for H1 type solution, but for H2 solution. So we are not able to show H1 of H1 alpha solution, but we go directly to H2 alpha. So this is like how you show the result. The questions now is we show existence of H2 solution, H2 alpha solution. Can we prove the regularity? And this is nothing. This is something that we can do quite easily by the fact that you have an analytic boundary condition. So basically, by the fact that you have an analytic, you put UR on the right hand side, and you see immediately that if you have a function which is H2, UR is in H3R, it means that the phi of U is in H3R, so U is in H3. I mean, you can get a derivative. But not only that, whenever you get a derivative, then you will move also in the weight. So for a weight lambda minus 1, you go to lambda, so you move on the right on the in the main variable. So what we get is something like this. So we start from a solution which is like leading this point. Then I can prove the regularity. So from this one, this is like a sort of H2 solution. I get in H3 solution, H4, H5, up that I meet this singularity. I mean, I can go outside of my yellow domain, but I can improve the regularity. And immediately see that if I choose alpha, theta really small and alpha really negative, then I can get how like really many derivatives. 1, 2, 3, 4, 5, you know. So basically, if the theta is very small, the solution is regular. So, what is the problem bit of this improved regularity result? Is that the waves, when alpha is positive, it controls the behavior of your function on the tip. So it means that if alpha is really big, if alpha is big, then this function will the function the space will tell you that the function will decay to 0 really fast, and actually to a polynomial level. And so, if you take a forcing term, and if you want to have the right hand side in this like sort of regular space, then this forcing term must decay to 0 really fast. And so what you can do, you take your forcing term, you write it like a Taylor polynomial in the tip, and you subtract it. So now this new forcing term is not anymore decaying to 0. This new forcing term F1 is decaying to 0 enough fast to be in the like sort of regular space, and then you need to add you have an extra polynomial. So basically, the final result that we have is about functions that are sum of some polynomial part plus some regular part. So these kind of spaces are called Kondratev spaces. And then also looks so the functional space will look like this. So basically, you decompose all the function, you split it like some polynomial problem plus some regular part. Your function u is also written like a regular part plus a polynomial part. And then what you can do, you define the norms like the sum of the polynomial part plus the regular part, and you can show existence of solution. And here the constants are dependent on theta. And the solution are regular. I mean, you can go up to to a certain k that depends on this number. So you immediately see that if pi is close to theta, then you cannot improve so much. But if theta is small, then you can improve the regularity quite a lot. So this is what we did. The question is what we are going to do. I mean, what we like to study is the evolution of the droplets. So what you should do is to introduce the derivative in time. So instead of studying the stationary stocks, you should start to consider the evolutionary problem. I mean, you have to have the derivative in time. So what are the good parts of what is the main difference? So the good part is that the derivative in time is more control of new scaling. I mean, you have a scaling for a fraction of u, you have a scaling for the t of u, and these two scaling are different. So you have more control of different scaling. What are the bad parts? Okay, in this case, by the fact that we are working only with the integral equation, you have existence, you are able to show existence in H2, H2 in intersect H1 and 2. So in the unweighted setting. But the bad part is that for this problem, the normal Laplacian has non-empty kernel when you choose lambda is equal to 0. So basically, in 0 there are functions that satisfy the normal Laplacian, which are non-trivial. And what is bad about about when you introduce the derivative in times, that after this trip to adding extra term in our bilinear form seems not working so well. I mean, before, basically to control the second derivative, you don't need to do integration by parts because you multiply just by Laplacian, so you don't need integration by parts. But when you have the t of u, if you multiply by Laplacian, you have some term, you have to do some integration by parts on u, and this will create difficulties. So let me show this picture. So basically, if you look to the integration in polar coordinate, so in polar coordinate you can write it in this form, and you see immediately that here there is a jump of 2 in the scale. So here is where you control basically the second derivative of u, and here is where you control the t of u. Okay? So what is happening? When you show existence of solution in L2, H2 intersect H1, L2, what is happening? That you see immediately that you are on the line where the non-Laplacian is as non-trivial kernel. It means that when you show existence in the unweighted setting for H2, H2, H1, H2 solution, then you don't even know which solution we are picking up. But the fact that you have two different scaling will let you, in some interpolation, you can say that somewhere here your solution is like H1 alpha, and for this solution you know that you have only one candidate, and you can ensure that the candidate that you construct is exactly the one that you want. So this is some good part of the system. What is bad is exactly this integration part. So if you look to the stock systems or even the Laplace equation, to get estimate on the second derivatives, you just multiply the Laplacian of u, and then you see that you have control of some second derivatives. You see here? And that's all. I mean, but if you want to do the same for the equation, then will appear then the t of u Laplacian of u. And here you have to do integration by parts. If you do some integration by parts, then some derivative will fall on the weights. And when derivative falls on the weights, you create terms that you are not able to control, although they are lower order terms. Why? Because if you are trying to think about the Hardy inequality, the Hardy inequality will have weights 1 over alpha to the square that will make stuff blow up. So you cannot, it's difficult to, lower order terms are not trivially controlled by the higher order because of the weights. I mean, the weights don't have a pointer inequality. And so what, let me write the conclusions that at the moment we are able to show a result of the following. So in the weighted spaces we are able to show existence of solution in L2, in some L2, H2 weighted spaces, and also the gradient is in L2, L2. But then the forcing term is some weighted L2 spaces, but we have to add some extra force, which we have to ask that the forcing term has some regularity also on the time variable. And what we are trying to understand now is why this is happening and why we are not able to do the result with only L2, L2. But of course this is something that seems difficult for the moment, and we don't know if we will be able to solve it soon. So thank you very much.
¿Alguna pregunta o comentario?
So, in the last project, the result is just for the integration. You have not divergence free condition.
No.
Okay. And the fact that the time norms are weighted, this means that you have to introduce because you have weighted H weighted.
I mean, actually we do a tree which is common. We go to Laplace. We go to Laplace, we introduce KU. So we treat it always like we see it always like a relative problem. So we forget immediately the derivative in times because we go to Laplace. So this one will be like a KU, where K is complex, and then we look for like an estimate of this type in the domain, the complex plane, like so you go to mainly to and then you look as well on like where case here, I mean case should be here. And so go ahead with the question.
No, waits also in time, so you
Yes.
need
Yes.
¿Alguna otra pregunta?
Yeah.
In the case, instead of stocks, you have Darcy's law.
Okay, for Darcy's law, okay, the lubrification approximation was started by Masbudi and Hans Knuffer. So they start from the droplet. So if you take the minus, U is equal, or with the minus, or I don't know. But I mean, if you start with a droplet of this type with Darcy law, you pass to the limit when theta go to 0.
Yeah.
Then you get the theta. And this was proven by Masbudi and Hans Knuffer. So this was done there. Like there's a paper, and for that law is done.
Yes, done. And to put stocks is more complicated.
And
to add the Laplacian to the velocity makes the things
the problem that I mean here we use some tricks, main tricks, and for the other one already like okay, I would like to have my name stocks here. Okay, I have my Navier-Stokes system here, and okay, can you show existence with a small time? Okay, there are no results. Then you should show that actually, if you are taking theta going to 0, then this time will remain enough big. I mean, you have many issues. I mean, you need to ensure, we expect that when theta go to 0, the time should increase. But I mean, in principle, you have to ensure that your local existence result is enough consistent to send the stuff to 0.
So, your use of manual transform is more motivated by dealing with the weight or by dealing with the boundary condition?
The wedge.
The wedge.
I mean, this is much simpler, and the fact that yes, because you're in the wedge is, is common to use weight, and also like in the paper in the books of there was motivated that actually when you are trying to solve PDEs and parabolic PDEs on the conical boundary, I think that one of the most common references are these books. Mm-hmm. And their tricks is really to go, if you have a conical point, you go in Mellin, and then there you will see that everything, if you choose the scaling variant boundary condition, then there is a way to solve this elliptic.
So in particular, could you do it, say, for Laplacian with Robin boundary condition?
Yes, this is easier. Yes. So yes, this is easier. I mean, we didn't write like we just went from this because here there are problems. But for the Laplacian view with the Robin boundary condition, I will say that I can do it without too much thinking. Because you introduce two linear form, you don't have so many integration by parts that will make appearing many bad terms that commutated with the width. So basically you are safe, you have enough room to do what you want.
Any other question or comment? So we'll extend Marco. Okay.